Today we're going to do a mini lab on the combustion of wax. So what is wax? Wax is a mixture of hydrocarbons. And remember that hydrocarbons are compounds that are made up of carbon and hydrogen. So we have various hydrocarbons that make up wax, but we are going to use a specific molecule as our representative particle of wax, and that is C25H52. Molecule wax is a big molecule. We have all these carbons bonded to other carbons, so we get long strands of carbons with hydrogens around them. And in a solid, you can kind of think of those molecules like strands of spaghetti that are all intertwined with each other. Okay, so we need first, before we do our lab, to discuss the difference between melting and combustion. So melting, this is a physical process. Whereas combustion is a chemical process. For melting, the formula stays the same before and after melting. The formula stays the same because we only have what is called a phase change. You're going from a solid to a liquid. When we have combustion, the formulas change. Because we have our reactants being turned into new products. The formulas of the reactants are different from the formulas of the products. So when we have this physical process, no covalent bonds are broken. No covalent bonds in the molecule are broken. So all the molecules, C25H52, stay the same. Here, in our combustion reaction, the covalent bonds in the reactants are broken and new covalent bonds for the products are formed. So covalent bonds are broken and formed. So let's write a chemical equation that describes our melting process for our representative wax compound. So that would be C25H52 solid. When we melt it, it becomes C25H52 liquid. Our formula stays the same. Our phase changes from solid to liquid. For combustion, we start out with C25H52, and it will be solid. And for any combustion reaction, we must have oxygen, so O2, as a reactant. And when you have what is called complete combustion, your products are CO2 and H2O. So I will leave you to balance that equation. You know how to do that. Even though we have these larger subscripts here, the process is the same. It's a CHO reaction, so balance your carbon first, then your hydrogen, and of course leave your oxygen till the end. All right, so you're going to balance that. So for our lab, we are going to do the combustion of wax. And our purpose is to calculate how many grams of oxygen are consumed, how many grams of carbon dioxide are produced, and how many grams of water vapor are formed or produced when a tea light burns for 1.00 hours. All right, so this is a tea light. That's what it looks like. And how are we going to do this? Well, to be able to figure out how many grams of oxygen are consumed, we need to know how many grams of wax get reacted. So I have a kitchen scale, and we're going to take the mass of our tea light, and then I'm going to light it. I'm going to let it go for an hour, and then we'll measure the mass again. And when we light it after burning, we will have less mass because some of the wax is going to form carbon dioxide and water vapor. Okay, so here is my kitchen scale. Oh gosh, you know what? Maybe we'll have to do it that way. Unfortunately, this kitchen scale only goes to the ones place, so we're not going to get good sig figs here. Oops, that's right, I have to turn it on first. Okay, so it is set to the unit of grams. Put on my tea light, and we can see that our mass is 11 grams. So let's make a data table for that. So this is our data table. So we need the mass of the tea light before burning. And we just saw that that was 11 grams. Okay, and then let's just make our next entry. We're also going to need the mass of the tea light after burning. Okay, so let's get our tea light there. And oh my gosh, I was going to use the timer on my phone, but my phone's already being used to film the video, so I guess we won't do that. Okay, so I'll just have to do the time. So I light my butane lighter, which, oh, there we go. Okay. All right, so our tea light is lit, and I am going to let that go for 1 hour, and then we'll come back and we'll take the mass and then talk about the calculations. Okay, we're back, and it's been an hour, so I'm going to blow out the light. So now we have a lot of melted wax that's in the tea light holder, but that has not combusted. That's still part of the mass. So we're going to go ahead and take our mass now. Okay, there's our scale, turn it on. Okay, to 0. Put on our tea light after burning, and we can see that we have 8 grams now. All right, so let's put that in our data table. So we have the mass of the tea light after burning is 8 grams. So that means the mass of the wax burned, the wax that was in the combustion reaction, is the missing mass. We started out with 11, we only have 8 now, and that's because 11 minus 8, 3 grams of wax were burned. Oops, went off the page there. 3 grams of wax were burned. And unfortunately, we only have one significant digit, one sig fig, because of the balance that I used. But you got to make do with what you got. Okay, so now we're going to use that data to answer the questions posed at the beginning of the lab. So let's go back to our chemical equation for the combustion. So C25H52 plus O2 yields CO2 and H2O. And of course, this is for complete combustion, which we did not have. For complete combustion, we would need a good blue flame As you saw, we only had a yellow flame, but we're just going to assume that we had complete combustion. And of course, you should have this balanced, so you should have coefficients in front of all your substances. So now we're going to answer our questions. I'm just going to set it up and then you're going to actually do the work. So the first question or purpose was how many grams of oxygen were consumed during the reaction? So that's our X. X grams of O2 were consumed when our 3 grams of wax were combusted. So the missing mass is what we're interested in for doing our stoichiometry. That's the amount that actually was in the reaction. So now you just set it up like any other dimensional analysis. So X grams of O2, set that equal to the 3 grams of C25H52 multiplication sign and crossbar. Okay, so the first thing you're going to need to do, change the grams to moles. So you're going to need to do a molar mass calculation for the C25H52. Then you're going to need the mole ratio using the balanced coefficients that you figured out. Then you're going to need a molar mass calculation for the oxygen. Remember, oxygen is O2. So for the molar mass, you need to consider 2 atoms of oxygen in one molecule. Okay, and when you do that, of course, we only have 1 sig fig here. You're going to have 1 sig fig for your answer. Then you're going to answer the next question. How many grams of carbon dioxide are produced? So now our X grams is going to be here under the carbon dioxide, and we're still going to use that 3 grams of wax for our dimensional analysis. So then the next setup will be X grams of CO2 equals 3 grams of C25H52. And again, you're going to need 3 conversion factors, grams to moles, mole ratio, and then grams to moles for the CO2. And then the next one, we want to know how many grams of water vapor were formed. So X grams of water vapor for the same 3 grams of wax. So that'll be X grams of H2O. Oops, I'm off the page. X grams of H2O equals 3 grams of C25H52. And then do your 3 conversion factors. So we have 1, 2, 3 dimensional analysis calculations to do to answer the questions for the lab. And that's it.